everyone, and welcome to my talk on how your brain is conspiring against you making good software. So, as was already mentioned, I'm an engineering manager at DigitalOcean, which is a New York-based company that tries to take the cognitive load out of managing your infrastructure. I'm also an organizer of Empire.js, which is a JSConf family conference in Manhattan, and that's organizing a conference is a lot of work. A lot of things go into it, so we just take a few minutes or a few seconds to give a round of applause to all the organizers and volunteers, because, yeah, they're awesome. So yeah, I'm also Zeigen Vector on Twitter, so if you want to tweet questions at me while I'm up here, I'll try to answer them as best as I can once I'm not up here anymore. I've also tweeted out the link to my slides, if that interests you right now. So before I was a JavaScript engineer, and way before I was an engineering manager, I studied cognitive science in university. Cognitive science talks about a lot of things like thinking, decision-making, attention, vision, consciousness, and my personal specialty, human language processing. But if you were to ask me to sum up what I learned in all those 4 years into one concise sentence, it would be that humans are predictably irrational. This predictably irrational phrase was coined by a psychologist named Dan Ariely, who in fact has a book by that title. But what does this mean, that we are predictably irrational? It means that we employ predictable tricks, patterns, and shortcuts that allow us to make more efficient decisions, to have what's called cognitive economy. But this fast thinking often causes us to deviate from rationality in our judgments, to make what two other eminent scientists in the field, Amos Tversky and Daniel Kahneman, have called severe and systematic errors. And these errors are called cognitive biases, which is a phrase that you might have heard of a few times. But this is a JavaScript conference and not a cognitive science conference, so what does this have to do with code, right? Well, my job as an engineering manager is to make sure that my team, which is comprised of humans, is happy getting their work done, getting along with each other, growing as individuals and as programmers, and it's also my job to grow my team to make it the most successful. My team is like my product. So I've started to think back to my cognitive science years, and I'm trying to figure out, especially how these cognitive biases and other quirks of our mushy human brains affect us as we're making software in the environments that we're making the software in. Because software isn't just about code. It's also about humans. Software isn't software if there's no one using it, I think. So yeah, I'm trying to think about these cognitive biases because even the most calculating software engineers is a human, and therefore subject to these cognitive biases, no matter how much they think that they are immune to the rationalities of humankind. So I'm going to talk about these things. And so first, I'm going to talk about logic. So one of the fundamental underpinnings of programming is logic. In programming, we have if statements, else statements, booleans, ternary operators, but computers can only do what humans tell them to do. And it turns out that humans are not very good logical thinkers. One of the tools that psychologists use to test this is called the categorical syllogism. We have one right up here on the screen. So a categorical syllogism is a logical argument with two premises and a conclusion. And scientists will ask humans, hey, does this conclusion follow from the premises? So I'll give you a few seconds to answer that question for yourselves. So when this was presented to participants, 81% of them said, yep, the conclusion follows from the premises. 10% said something else wrong, and only 9% of people got it right. So that's not great. And reasoning about complex if-else statements isn't much better. So a psychologist named Weissen came up with a task involving 4 cards, in which every card has a letter on one side and a number on the other side. And participants were asked to evaluate this rule. If a card has a vowel on one side, it has an even number on the other. And then asked the participants what cards need to be flipped over to make sure that this rule checks out. So formulate your own answer. So only 4% of people got the right answer, 4%, which is to flip only the A and the 7 over. And if you're stumped about why this is right, remember that the rule says nothing about what has to be on the other side of consonants. So what does this mean for testing our code properly, right? If we can't come up with questions to test rules that we hold to be true, how are we going to test our code, and what type of bugs are going to arise from this, right? But luckily, there's some hope, which is that we get much better about reasoning about concrete examples. So some other scientists adapted Wayson's 4-card task to test a concrete rule, which was that if a person is drinking beer, they must be over 19 years old. And in this case, 73% of people got the right answer. So an improvement, but still not great. So when we inevitably make a mistake in our code, logical or otherwise, because after all, we are humans, we're going to have to end up debugging our code. And as computer science celebrity Brian Kernighan said, debugging is twice as hard as writing the program in the first place. So why exactly is debugging so hard? I think there are some cognitive biases that will help, or not helping us to debug well. One of them is the confirmation bias, which is that we have a tendency to search for, interpret, favor, and remember information in a way that confirms our pre-existing beliefs or hypotheses. We also give disproportionately less consideration to alternative possibilities. So an experiment to test this, Wayson did it again. And so for instance, they gave participants a trio of numbers, like 2, 4, 6, and told the participants that the trio conformed to a specific rule. And their job was to figure out what the rule was by asking if other trios also conformed. The rule in this case is actually pretty simple, that the numbers just have to be in ascending order. But people ended up having trouble, especially when they asked only confirming questions and not disconfirming questions. If you were to say, oh, I got the rule, it's does 6, 8, 10 apply? Yep. You would probably just keep going down the same path. But if you're I'm going to try something different, 1 to 1,000,000, and they said, yeah, that also works, then you have more insight into what the rule actually is. But we tend to scrutinize disconfirming evidence. We try to find flaws or ambiguities in this evidence, blaming, say, when it relates to code, a bug in the library, or it was someone else's code that has the bug in it. And even when the facts are clearly stacked up against the belief that we are holding true, we often throw out those disconfirming facts, especially when the issue is emotionally charged, such as when your code has a bug in it. We also tend to be rigid in how we approach problems. So if you wrote the code, you're going to be rigid in thinking through the problem, and it's going to be harder to think outside the box and squash the bug, especially if it's on a conceptual level. I know I'm guilty of substituting a single equals for triple equals, and even that type of bug is hard to find. So when the bug is on a more conceptual level, it's that much harder to find and squash. And we even sometimes tend to block problem solutions based on past experiences because we have an inability to see problems from a fresh perspective. And I think a great way to get around this is to pair on squishing bugs. So you get that extra set of eyes when you're particularly stuck. Another thing that's so frustrating about debugging is that sometimes it feels like there's no end in sight. Right? You're just searching and searching, and you're like, why is this not working? And it's frustrating when there's no light at the end of the tunnel. And this is because we often have no idea when we're going to solve a problem, even the 30 seconds before we end up solving it. And so to test this, scientists gave subjects insight problems, kind of like word problem, brain teaser type things. And as they solved the problem, the scientists asked the participants to rate their progress in terms of warmth. So how close do you think you are to solving this? Initially, they gave ratings of 1 to 2, and then their warmest rating abruptly spiked when they got an answer, whether or not it was correct or incorrect. Breaks are also more important than you think when you're trying to solve a problem. And I know when I'm trying to squash a bug, I'm dead set on trying to solve that. No breaks until I finish it. But breaks are actually really good, and scientists think that this is because it helps you forget misleading hints. So to test this, psychologists gave participants some puzzles to solve, as well as misleading hints. The control group had a minute without breaks to try and solve the problem, and the experimental group had 30 seconds, or interrupted for a short bit, and then had another 30 seconds. The interrupted group actually did better, and it was found that the group were actually less likely to remember the misleading clues, suggesting that maybe these two things were correlated. Creativity is also kind of like feels like it's involved in squashing a bug or in problem solving. But what exactly is creativity? Well, scientists think it's really actually nothing special. It's just when the sum of all your experiences, memories, training, and motivation come together in the right way to give you the right tools to solve the problem. All right, so now that we are writing our own code and finding the bugs in it, and maybe there's some people helping us, we've entered into this realm of working with other humans, and maybe even trying to read and use other people's code. But this is hard because, again, we tend to think about problems in fixed ways. When you're reading someone's code, kind of like you're getting into their head, right? You're seeing how they solve the problem, and that is unlikely to be exactly the same way that you would have solved the problem. So therefore, it's harder to understand what they're doing, therefore makes it that much harder to read the code. Also, we tend to use other people's code when we're using libraries. But y'all might have heard of the not invented here syndrome, which is that we're kind of averse to using things that we didn't write. Cognitive scientists have called this the IKEA effect. It's a fairly new phenomenon. Scientists asked participants to assemble IKEA furniture, build Lego contraptions, and fold origami. And then they were asked how much money they would pay for their creations, as well as for experts' creations. And participants were willing to pay the reasonably same amount of money for their finished, amateurish, dilapidated paper cranes as they were for beautifully folded, professionally folded origami cranes. And while this particular experiment was mainly about money, I think it's fair to extrapolate to value in general, and how much we value other people's code versus how much we value our own. So that's why we don't want to use that library that has been battle tested and seen bugs have been fixed through lovely open source processes and have been used in ways that may be similar or different from the way that you're going to use it. So working with other people, maybe you're on a software team, and therefore you probably have to do sprint planning or something, or tell someone how long it's going to take you to finish that bit of the project. My job as an engineering manager is to make sure that my people get their work done in a reasonable amount of time. But there's something working against me, which is that we're really bad at making predictions about how much time it's going to take to do something. And this is called the planning fallacy. So an example of this was some psychologists asked 37 psych students how long they thought it was going to take them to finish their senior theses. And the average estimate was about 34 days. But the actual average time that it took these people to finish their papers was about 56 days, with only about 30% of people finishing in the time that they predicted. And this phenomenon occurs regardless of if people know that past tasks that were similar also took them longer than they expected. Didn't really matter. And this also really only happens for our own tasks, whether we're working by ourselves or in a group. For other tasks, for other people's tasks, we show a pessimistic bias. We think it's going to take them longer than they say. And this is part of a larger bias called the optimism bias, which is that we think that bad things are more likely to happen to other people than to us. And this is seen in a wide array of situations, not just planning our software projects. So people tend to think that they are less susceptible to crime than other people, or less susceptible to the whims of the stock market, all sorts of things. So yeah, we're not really great at that. We're also often so worried about wasting time that we've already spent and invested resources in that we don't consider the cost that it's going to take to continue doing something that's slogging. So this is called the sunk cost fallacy, and I think it's contributing to us wasting a lot of time in things that are just taking a really long time. So once you've been through that sprint planning meeting that took 3 hours, you probably have to go back to your desk and start working. maybe in an open office, so the person like right next to you is on a Google Hangout with the person right next to them. So there's a lot of noise, and this isn't really the best for productivity, but in the grand scheme of things, we're actually pretty good at filtering out unwanted stimuli, and this is called selective attention. Scientists like to study selective attention by doing what's called a dichotic listening task with shadowing. So participants have two speech streams or sound streams going into both of their ears. So in one ear, participants will get a stream of speech that they're supposed to repeat back, and in the other ear, they get speech, music, something. They're not supposed to pay attention to that. And when questioned afterwards, participants generally have very little recollection of any semantic content that they weren't shadowing. So the purple, oh wow, that contrast is off. So yeah, like a switch from English to German goes unnoticed. Like you could tell them things that they don't want to hear, they won't remember. But physical attributes of sound are remembered. So people generally are able to recall if the unattended channel is speech or not. So like in your office, there could be like music playing. You'll know that there's music playing, but maybe not listen to the lyrics. But when you're listening to the lyrics, you're probably not going to be able to focus that much on writing code. But if there's something salient in the speech stream that they're not listening to, like their name or some like not safe for work words, people usually notice them, and this is called the cocktail party effect. So this suggests that selective attention requires both ignoring, like active ignoring, and active paying attention. And so just because we're good at selective attention doesn't mean it's good for us. We're putting in like active mental effort to blocking out things that we don't want to be paying attention to, which means that there are less mental resources going towards the stuff that we actually need to be doing. So we can only pay attention to so many things at once, mostly one thing. We have a limited supply of mental resources, and we often don't have the budget to do more than one thing at once. So you're unlikely going to be able to keep writing that difficult algorithm if you're trying to listen into that conversation happening 10 feet away between your engineering manager and your product manager, that if the project you're working on with that algorithm is going to get scrapped tomorrow. Not going to be able to concentrate. And this is because we are sometimes helpless to the processing power of our brain, because our brain just does things automatically in an attempt to be efficient. So if you had an email account anytime around the early 2000s, this might look familiar. And this is actually real science. It's called the Stroop task. And if you're not familiar with it, the idea is that you're supposed to say the color that the word is written in, not the word itself. And the leading theory about why this occurs is called automaticity. So reading is an automatic habitual process that we don't really have to think about very much. But recognizing a color isn't an automatic process. So while reading doesn't need controlled attention, it uses enough resources to reduce the amount that we can then dedicate to saying what color the ink is. All right, so as I said before, software is actually about people. And this lovely phrase comes from the amazing people at And Yet. And so when I heard this, it kind of like changed the way I thought about software and about engineering management. Like, it's not just about the code. Again, I said this in the beginning. It's also about the people. And without humans, what's the point in writing software? So now we're going to start to get to the human side of all this, right? Something that's getting in the way of us being productive on our teams, I think, is that relatively unskilled people think that they are better at tasks than they actually are. This is called the Dunning-Kruger effect. And funny story, it was inspired by the case of a dude who robbed 2 banks after covering his face with lemon juice. Since lemon juice can be used as invisible ink, he thought it would cause his face to be invisible on the security cameras, which is unfortunate, I guess. And this is part of a larger phenomenon called illusory superiority, which is that we tend to overestimate our own skills and abilities. So we think that we're higher in intelligence, we're going to be better at performing tasks and tests. We think that we have more desirable traits and characteristics than other people. But so an example of this was in a survey of faculty of the University of Nebraska. 68% of these teachers rated themselves within the top 25% for teaching ability, and more than 90% rated themselves as above average. But like that doesn't math. Like 50% of people have to be below average. That's just how it works. And like, well, like all of you are below average in something. Like I'm below average in height. So like, doesn't mean that you're bad at what you're doing, just below average. So like, how is this getting in our way, right? So you're not going to make good software if you don't realize how much more you have to learn. If there's ways that you can make your software better, but you're not really open to learning them because you think you're the best, your software isn't going to be good. So there's the flip side of this, which is that skilled people often underestimate their abilities and think that tasks that are easy for them are easy for others. So if you've been doing this for a while, you might forget what it was like to be a beginner. You're not going to have empathy for the beginners on your team that are actually integral to your team. They're going to ask questions that are important to making good software. They're going to ask the things that you're not really thinking about anymore. So if you dismiss their questions, they're not going to ask them anymore, and then your software isn't going to be as good as it could be. But this can also manifest in a different way. And if you attended the last talk on imposter syndrome, you know what imposter syndrome is. The short of it is that people sometimes think that their accomplishments and their achievements are the result of luck, timing, deception, like they pulled the wool over someone's eyes, they don't deserve what they have. When in fact, they probably do. And some studies suggest that this is particularly common among high-achieving women, but across the board, even some of the best programmers I know suffer from imposter syndrome. So we're working with people, and we're working with the team. So how do we assemble the best team? And how are these cognitive biases getting in the way of us assembling the best team possible? I think one of the things getting in the way is that we tend to favor members of our own in-group. So, and this is getting in the way, especially with those like referral bonuses, right? You get a lot of money for referring people in your social circles that you think are good programmers. But if our social circles tend to look like us, you're just going to refer them. So if I were to refer people who looked like me, my team would just be a bunch of white women, and that's not good either. So we want to not do that. So another thing getting in our way is called the fundamental attribution error. So people have a tendency to attribute situations to other people's character rather than to external factors. So a classic example of this is like you're driving down the street, being all law-abiding and driving the right speed limit, and then all of a sudden someone like rushes past you, and you're like, what a jerk. They're like breaking all the laws, and they're causing a dangerous situation on the road. But maybe in fact they're driving a loved one to the hospital, and they're not really thinking about laws. They're just thinking about their loved one in the backseat. So if you were in that case, you would know to have empathy for that person, and it has nothing to do with they're not like a jerk, actually. So this also happens on a larger scale in something called the group attribution error. So people have a tendency to believe that attributes of a group member reflect the entire group. So I thought this was well explained by this XKCD cartoon. So on the right, you see two dudes, and that's actually on the left. I'm below average in which direction is which. So on one side, you see two dudes, one who apparently is not great at math, and his friend is saying, "Wow, dude, you suck at math." On the right, we see a dude and a woman, and the woman apparently is not good at math, and the guy is saying, "Wow, girls suck at math." So why is this kind of true? Well, studies have shown that the group attribution error is stronger in perceptions of groups that are viewed as more dissimilar to one's own. And this doesn't really happen with perceptions of our own groups. So decisions made by people in our own group are the result of structural constraints, but decisions of other groups are the result of their attitudes. So in tech, perhaps it's not that certain groups of people don't want to be programmers. Maybe, just maybe, there are structural forces making it harder for them to do so. Something else that I think is getting in our way is called the availability heuristic. And this, like the popular example of this is that, like, why people are so afraid of plane crashes, which is like we hear only about plane crashes and not successful plane trips. So those examples of unsuccessful plane trips are more salient in our mind, and therefore, like, the plane's going to crash. So I think this applies to our programming communities, and that, like, if we are surrounded by people who all look a certain way, and if the prominent members of our community, the main contributors to open source, and the people who we see on stage all look a certain way, we're going to start to think that those are the people in our community, and those are the only people in our community. And those are the only people who can contribute to open source, and the only people who have good ideas to talk about on stage, which is not necessarily true. Something else that's also getting in our way is called the representativeness heuristic, which is that essentially that we think that categories are relatively homogeneous. So if someone is a software engineer, we expect them to have the traits that we associate with a software engineer, and vice versa. And this heuristic leads to several biases, such as something called base rate neglect. So Tversky and Kahneman ran an experiment in which they gave descriptions of a group of people, so 100 people, and 70 are lawyers and 30 are engineers. And they found that participants often said that someone who sounded like an engineer was more likely to be an engineer, even though the probability was against that because there were 70 lawyers and 30 engineers. I've seen this come true at programming meetups. It's both happened to me and to my friends, where we're at a programming meetup. It's very likely that people at programming meetups are programmers. But people have come up to me and been like, are you a designer? Are you a recruiter? I'm like, no, I'm at a programming meetup. I'm a programmer. It's like not good. So might have been able to tell I'm kind of talking about diversity here. So like, why is diversity important for assembling a good team and creating good software? Well, so I mentioned that creativity is all about associative memory. So when you have a diverse team, you're going to have a wider array of experiences, of backgrounds, of interests, and therefore, you're going to have better collective associative memory. And therefore, you're going to be more creative, you're going to find better solutions to problems. That's going to lead to better software. So what can we do about all of this, right? So first off, like, don't feel bad. Your brains are, like, literally programmed to do this. Because, like, back in the day, we were just supposed to, like, escape predators. But now we are sitting at computers thinking all day, so it's a little different. So like the quicker that you can think, the quicker you're going to get away from that tiger that's chasing you, and you're going to have more cognitive economy. So this thinking fast system is called System 1 in the literature, and the thinking slow system is called System 2 in the literature. And if you might have read a book or heard of a book by this title, Thinking Fast and Slow, by Daniel Kahneman. So, like, what can we do about this, right? Like, as I said, we are literally sitting there and thinking. Our job is to think. And we usually take a really long time to think through very hard problems. So if we just take that same amount of time and apply them to things that we might not think about as much, we just take another hour to make those hard decisions, then we're probably going to end up making better software that more humans can use, and we're going to end up making these things with happier humans. So thanks for listening. That's me and all my emoji friends. You can find my slides at that link. Tweet at me at Zeigen Vector, and thanks.